Hello. So in this video we're going to talk about other limit evaluation techniques. So we've already covered the basic limit laws, things like the sum and the difference rule, the constant multiple rule, the constant rule, the identity rule, the quotient rule, the product rule, power rule, and the root rule. You may remember that the quotient rule in particular only worked when the limit of the denominator was not equal to 0. We're going to explore, well, what do you do when your denominator would be equal to 0 and you would be unable to use the quotient rule. So let's go into writing mode. Okay, so we're going to motivate this with an example. Let's say you wanted to do the limit as x approaches 1 of x squared minus 1 over x minus 1. So you would try to use the quotient rule. Oops, sorry. You would try to use the quotient rule and you would break it up. You'd get the limit as x approaches 1 of x squared minus 1 divided by the limit as x approaches 1 of x minus 1, and then you work on the denominator. So the limit of x minus 1, that's a difference, so you can split it up into the limit of as x approaches 1 of x minus the limit as x approaches 1 of 1. The limit of x as x approaches 1 is 1. The limit of 1 is 1, and you get 0. Alternatively, I guess you could have used direct substitution, and you would have gotten 1 minus 1, which is 0. Let's put by direct sub for by direct substitution. But either way, the bottom is equal to 0. You can't do this, but not equal to each other. So what what do you do? So I'm going to open up a Mathematica, and actually will give us an interesting idea about what you can do sometimes in this situation. Come on, Mathematica. Load. Okay, there we go. Let's switch the window. Okay, so let's define our function. F of x will be equal to, we had x squared minus 1 divided by x minus 1. And what we're going to do is plot this function. And let's plot it from, let's do negative 4 to 4. Oops. So you look at this and you're like, x squared minus 1 over x minus 1. This actually looks like it's a line. It seems to have a slope of 1, and it seems to have a y-intercept of 1. So let's make that function. Our g of x will be equal to x plus 1, slope of 1, y-intercept of 1. And what you can do is actually plot several functions at a time if you put the curly brackets. And you can actually see that they literally graph the same on top of each other. So these two have the same graph, basically, and I guess we'll do them separately, just so you can see. So there's the plot of f. There's the plot of g. You can see that they look exactly the same. There is, however, one crucial difference between them. So I'm going to copy the graphic, and we're going to go back to, what's it called? OneNote. So 1 second while I paste it in there. There we go. Okay, there's the two graphs. I'm going to call this one, this is going to be the graph of x squared minus 1 over x minus 1. This one over here is going to be the graph of x plus 1. Now the crucial difference between them, and I guess we'll call this one f of x, and we'll call this one g of x. They look very similar, but f of x is not actually equal to g of x. They are slightly different. The difference being that f of x is undefined at x equals 1, right? Because if you plug in x equals 1, you get a denominator of 0. So at x equals 1, which is right here, there should be an open circle. However, at 1, for g of x, it's a closed circle, it's defined. And this phenomena actually has a name, because they're literally the same except for at that point. So we call this agreeing except at a point. So what we have here is that f of x equals g of x almost. They're equal except when x is equal to 1. As long as x is not equal to 1, you plug it in and get the same value. And this is important because you can see from the graph that as you approach 1, the behavior of these two functions is the same. In other words, the limit as x approaches 1 of x squared minus 1 over x minus 1, you can see that it approaches a value of 2, and that's the same thing for the limit as x approaches 1 of x plus 1. And this actually always happens if f of x and g of x agree except at a point a, x equals a, then their limits as x approaches a of these two functions are going to be equal to each other. Let's just say they're both equal to L. So what's interesting about this is that we had no way to solve the limit of x squared minus 1 over x minus 1 because the quotient rule didn't work because we got 0 in the denominator. However, you can calculate the limit of x plus 1. You can calculate it using direct substitution. Right? If you just plug 1 into your polynomial x plus 1, you get 2. Okay, so usually this is how it's going to work. You're going to be given a limit for which you are unable to evaluate it because the quotient rule would not work. What you're going to need to do is somehow find this other function, g of x. So you'll start with this one, f of x. You can't evaluate it. You're going to somehow find a function that agrees with the one you started with, and you will be able to evaluate it. So there are some techniques that you can use to do this, basically. And it involves factoring and canceling, usually. Let's see why. So we started with our f of x equals x squared minus 1 over x minus 1. The top factors into x plus 1, x minus 1. And now you look at this, you're like, oh, those x minus 1s cancel. And what are you left with? That was that g of x. So your g of x equals x plus 1. That's the function that agrees except at x equals 1 with f of x. So let's do an example of this. Okay, so let's do the limit as x approaches 3 of x squared minus 3x all over 2x squared minus 5x minus 3. Okay, so we're starting off with our f of x. This is the function we're given, which is x squared minus 3x over 2x squared minus 5x minus 3. You can see that the top, you can factor out an x, and you get x times x minus 3. Now, if anything's going to cancel, it's probably that x minus 3. So let's divide out that x minus 3. You can use synthetic division. So you could put a 3. We put a 2, a minus 5, and a minus 3. The 2 goes down. 2 times 3 is 6. Negative 5 plus 6 is 1. 1 times 3 is 3. You get a remainder of 0. So that means that this factors into 2x plus 1 times x minus 3. And then you're like, oh my god, there we go. Those x minus 3's cancel. The remainder is going to be your g of x, the function that agrees except at a point, which is x over 2x plus 1. So I'm just going to write f of x equals g of x except when x is equal to 3. Right? Because if you plug in 3, f is undefined. Okay, so they agree except at a point. Now, because they agree except at a point, you know that the limit of your original function is going to be equal to the limit of your new function, so you can just take the limit of 2x plus 1. Now, because this is a polynomial, you can now just do direct substitution. You plug in the 3, 2 plus 3, 2 times 3 plus 1 is 7. So 7 is what your original limit is equal to. Boom. Okay. So a very common technique, you start with your f of x, you factor, stuff cancels, what you are left with agrees except at a point. We know that if two functions agree except at a point, then the limit of those two functions is equal to each other, right? The limit of f equals the limit of g. You calculate g by direct substitution, and you're done. There's another technique you can use to get this done that it doesn't involve factoring and canceling, but it's pretty similar. Let me show you how to do this one. So we're going to have the limit as x approaches minus 1 of the square root of x plus 2 minus 1 over x plus 1. So you look at this, you can't do direct substitution because plugging in negative 1 would give you 0 on the bottom. You're not going to use the quotient rule. And also, you can't factor anything. That square root of x plus 2 minus 1 quite simply does not factor. So you're like, what am I supposed to do? My f of x is square root x plus 2 minus 1 over x plus 1. And you're like, I can't factor and cancel. So you might remember the conjugate from pre-calculus. The square root of x plus 2 minus 1. The conjugate of that is square root x plus 2 plus 1. So if you multiply by this, it's the same as multiplying by 1. So you're multiplying by the conjugate. An interesting thing happens. So on the bottom, you get x plus 1 times square root x plus 2 plus 1. Now on the top, when you multiply it through the two square roots, cancel the square root, and you're left with x plus 2 minus 1. X plus 2 minus 1 will now become x plus 1. And notice you have an x plus 1 times square root x plus 2 plus 1. Those x plus 1's cancel. And remember, the x plus 1 was the offending term that made it undefined when you were negative. So you have now found this is your g of x. Your g of x is going to be equal to 1 over the square root of x plus 2 plus 1. This f of x that we started with and this new g of x that we got by multiplying by the conjugate and canceling, they agree except at a point. F of x equals g of x except when x is equal to negative 1. They agree except at a point. And because they agree except at a point, you know that their limits are equal to each other. So this up here was the limit of my f of x. That's going to be equal to the limit of my g of x. So the limit as x approaches minus 1 of my g of x, which is 1 over square root x plus 2 plus 1. Now, looking at this, you can use direct substitution, because when you plug it in, it's defined. So you get 1 over the square root of negative 1 plus 2 plus 1. The negative 1 plus 2 is just 1, so square root of 1 is 1. 1 plus 1 is 2. So you get 1 half. The limit of the original function was 1 half. Okay. Oh, shoot. I almost dropped this. Okay. So let me do one more example where we're going to use some one-sided limits. Or sorry, we're going to use a piecewise function, my bad. So let's do this as an example, because these get a little tricky. So example, let's say that we have this function f of x equals, so it's going to be a piecewise function, 4x minus 3 if x is less than 2, and then it's going to be x minus 3 squared if x is greater than or equal to 2. Okay, we're going to calculate a limit. We're going to do the limit as x approaches 2 from the left. We're also going to do the limit as x approaches 2 from the right. And then we're also going to figure out what's the limit as x approaches 2, period. Okay, so Wolfram is going to help us out here. We're going to use it to make the graph. So let me switch over. Oops. Oops. Okay, so we're going to define our f of x. Remember, we can make a piecewise function. We put it in curly brackets, and we put the two pieces in curly brackets. We have 4x minus 3 if x is less than 2. And then we have x minus 3 quantity squared if x is greater than or equal to 2. And let's plot this function. Where the x's shall go between, let's say, 0 and 4. See how that looks. Oh, there we go. Maybe 0 and 5. 0 and 6. There we go. Oh no, we could do 0 and 5. Okay, so I'm going to copy the graphic, I'm going to paste it back in, and we're going to use it to help us. So bear with me for a moment while I copy it over. Okay. Okay. So it's 4x minus 3 if x is less than 2, which means that this is an open circle right here, you know, for the part going to the left. This is a closed circle right there. We're missing that in the graph. Wolfram does not do it automatically for you, but you can easily figure it out by looking at the piecewise definition. And let's calculate what this value is. If you plug 2 into 4x minus 3, you get 2 comma 4 times 2 is 8. 8 minus 3 is 5. So this point right here, the open circle is 2 comma 5. If you plug 2 into the other part of the function, 2 minus 3 is negative 1. Negative 1 squared is 1. So this is 2 comma 1. Okay, so if we approach 2 from the left, that means we're following a string of points that looks like this. Those y values are obviously heading towards 5. Okay, what about if we approach 2 from the right? Well, you get these red points. The y values of those points are obviously heading towards 1. Okay, which means that this regular limit does not exist, because if you recall from the one-sided limits video, the regular limit only exists if the one-sided limits go to the same thing. So that's how you would do it graphically, but I want to talk about how would you do this analytically with the limit laws. So I want to calculate the limit as x approaches 2 from the left of f of x. Well, we know that if you're approaching from the left, you need to evaluate the function 4x minus 3. And you can just get rid of the one-sided limit, right? If you're approaching the values of 2 from the left, we were on the part of the graph that looks like 4x minus 3. Now, because that's a polynomial, you can just do direct substitution. You get 4 times 2 minus 3, which is 5, which is exactly what we got. Same thing if you want to do the limit as x approaches 2 from the right of your function. Well, if you're approaching it from the right, that's just the same thing as calculating the limit of the part of the graph on the right, which is just x minus 3 squared. That's a polynomial. You can do direct substitution, and you get 2 minus 3 squared equals negative 1 squared, which equals 1, which agrees exactly with what we had. Okay, so thank you for watching this video about alternative limit techniques. To summarize, the idea is that sometimes the quotient rule doesn't work. What methods do you have available to you? Well, basically, you're going to find a function which agrees except at a point, and you're going to have usually 2 different ways to do that. It might involve factoring and canceling. It might involve multiplying by a conjugate and canceling. Okay, thank you.